Now, we are going to start with proposition 1, the probability of the complement event. And we are going to move to the proposition 2 and proposition 3. Proposition 1 states that the probability of the complement event can be calculated as 1 minus the probability of original event. So you see, if you are interested in the probability of an event's complement, that is going to be 1 minus probability of E. Actually, this proposition is very easy to understand. However, we are going to show its proof in any way. But let me explain it. If I tell you that there is a 0.30 chance tomorrow to rain, okay, so the probability of raining tomorrow is 0.30, and if I ask you what is the probability that it is not going to rain, I mean, anybody that has logic should answer it should be 0.70, right? If there's a 30% chance for raining and there is a 70% chance for not raining, right? So why do we say that? Because of this proposition. So the probability of the opposite event, the complement event, because it contains every other outcome in the sample space, is equal to 1 minus the probability of the original events. Now, how can we prove that? How can we say that this equation can always be used? Now, after showing the proof, please do not forget that we are going to use this equation or the calculation of the complement event probability very, very, very frequently in our future courses. So the proof is as follows. Now, you know that the complement events, E and E complement, are disjoint events, right? So we know that. You know the third axiom that we have repeated, the additivity axiom. We have said, according to the additivity axiom, if we have two disjoint events over the same sample space, the probability of their union will be equal to the sum of the individual probabilities, right? The probability of E plus probability of E complement will be equal to the probability of the union. Why? Because E and E complement are disjoint events by nature. They do not have any common elements. And we also know the probability of E union E complement should be equal to 1 because the union of E and E complement gives us the sample space. And according to the second axiom, the unitarity axiom, probability of the sample space should be equal to 1. Now, according to the above equation, which is actually forced by the additivity axiom, in the second equation here, which is forced by the unitarity axiom, we can combine these two facts and say that the probability of E plus probability of E complement must be equal to 1. And accordingly, we get the above equation. The probability of the complement event is equal to 1 minus probability of the original event. You can also calculate the probability of an event using the probability of its complement as well. So this equation can be used in two different ways. Now, that proposition is very important for us, but we are going to practice this proposition in many, many different examples in our future classes. So at this point, let's skip to proposition 2, for which we are not going to show any proof, and it is just going to be left as an exercise. Now, for any two events, E and F, in the same sample space, they can be disjoint, they may have an intersection, it does not matter, okay? It says in the same sample space, we are defining any two events. The probability of their union is going to be equal to the probability of the first event plus the probability of the second event minus the probability of their intersection. Now, we are not just proving this proposition, but actually this is also a logical proof that we can do. I mean, you remember, if you want to develop the union set in set theory, first you put every element inside E, inside the union set, and you put every element inside F again, right? Then, because you have put the common elements twice, you remove one of these common elements. Or if you want to count the number of elements in the union set, you sum up the number of elements in the first set with the number of elements in the second set. However, because you are counting the elements in the intersection twice, you need to subtract the number of elements in the intersection for once, right? So by using this logic, we can also state that the probability of the union of two events is equal to the probability of the first event plus the probability of the second event, and we subtract the probability of the intersection event. And this equation is always true for any two events in the same sample space. As we have mentioned in the additivity axiom, this formula is only true when their intersection is empty. And this formula is always true, whether they have an empty intersection or non-empty intersection. So this is the second proposition, is the formula that we need to use. Now, actually, if these two events are disjoint, then their intersection will be empty. And what we know from the axioms, the probability of the empty set will be 0. In that case, this equation will get in the form of the third axiom. So please do not forget this equation provided by the second proposition help us to calculate the probability of the union of the two events. Now, another thing that I should mention here, though in this proposition, this formulation may seem like it is something that helps us to calculate the probability of the union by using three other probabilities here, the probabilities of individual events and the intersection events. Actually, in this equation, if you have any three values, the fourth value can also be calculated. So what you can also write is the probability of the intersection here can be calculated by summing up the probability of event E plus probability of event F and subtracting the probability of the union. Okay, so we can use this equation in order to calculate any probability inside this equation if we know the other three probabilities. Please do not forget about this. This is not a one-way formulation that only calculates the probability of the union event. Now that we have proven these propositions, assuming this we have proven the first and the second proposition, we are going to use them to solve a question. Jane is taking 2 books along on her holiday vacation. With probability 0.5, she will like the first book. With probability 0.4, she will like the second book. And with probability 0.3, she will like both books. So the question gives us this interesting information. So there is a chance for Jane to like her first book, that is 0.5. A chance also to like the second book, that is 0.4. And with 0.3 probability, she likes both of the books. So the question is asking us this probability. What is the probability that she likes neither book? What is the probability that she likes neither book? Now, before moving further to the solution, please listen to me very carefully. If you are going to solve a probability question, what you need to do is definitely, first, you need to write down given information in the question in mathematical representations. So what is the given information in mathematical representations? What is being asked in the question? Then you can move to the solution part. Now, for a simple question like this, obviously, it may not be necessary to write down all mathematical expressions to solve that. Okay. However, in homework assignments or in the exams, the questions that you are going to solve are not that easy questions. And if you want to be efficient, you definitely need to express the given information in mathematical terms. Also, as an engineer, this is our common language. So mathematics, mathematical expressions, mathematical representations are our common language to explain our solutions to each other. So for communication purposes, an engineer needs to learn the mathematical expressions in probability. Okay? So I need to warn you at this point. If you do not try to learn to represent the given information in mathematical expressions, or if you resist to do that, if you think that you are clever enough to solve a question without expressing it mathematically, I mean, I need you to think twice about this. So for every probability question, always start with explaining the given information in mathematical representations. That is half of the solution of the question. So here I am going to do this. First of all, the first sentence says that she will like the first book with 0.5 probability. So I'm going to define this as an event. And I will say that B1 is the event that Jane likes the first book. And what is the probability of B1 according to the question? It is 0.5. And the second sentence says that she will like the second book with probability 0.4. Now I'm going to define another event. B2 will be the event that Jane likes the second book. And according to the question, the probability of B2 is equal to 0.4. Now another information is given as she will like both books with probability 0.3. Now, am I going to define another event for the fact that she likes both books? Actually, no. These B1 and B2 are just sufficient to define this event. So the fact that she will like both books means B1 intersection B2. Both events are occurring at the same time. And according to the question, the probability of B1 intersection B2 is equal to 0.3. Now, what does the question ask me? The question asking me the probability that she likes neither book. How can I represent this event? She likes neither book. The fact that she does not like the first book is B1 complement, right? And the fact that she does not like the second book is B2 complement. Therefore, she likes neither book is represented by B1 complement intersection B2 complement. And according to the De Morgan law, B1 complement intersection B2 complement is also equivalent to the complement of B1 union B2. Now, B1 union B2 means what? The union event means she likes at least one of these books, right? And its complement is the fact that she likes neither book. Now, the question is asking me this probability. How can I find the answer for this probability? I'm just going to use my first proposition. According to the first proposition, the probability of the complement event is equal to 1 minus the probability of the original event. Right? So the probability of the complement of B1 union B2 is equal to 1 minus the probability of the union of these two events. Now, how am I supposed to calculate the probability of this union event? By using the second proposition, the probability of the union of the two events. Now, what is the probability of B1 union B2? It is equal to the probability of the first event plus the probability of the second event minus the probability of the intersection event. All these three probabilities are already given as an information by the question. So the probability of the union is going to be equal to 0.5 plus 0.4 minus 0.3, which is 0.6. Now, once I have calculated this value, I will plug that value here in place of probability of B1 union B2, and my final answer will be 0.4. Basically, I can say that Jane is going to like neither of the book with 0.4 probability. Now, this question was just your first question. And actually, it is a very simple question. However, the aim of this question is not to solve it. The aim is basically how can we use the propositions about probability in the solutions explanation. So remember, always you are going to explain your solution by using mathematical expressions. Therefore, this is a nice question where we express solution in mathematical terms. Please try to solve your questions in this form. Now, in the third proposition, we have a generalization of the second proposition. So instead of calculating the probability of two events, what if we want to calculate the probability of the union of three events? So let's just say we have E, F, and G defined in the same sample space. What is the probability of a three-way union here? Actually, Following from the second proposition, we can generalize it by defining the probability of the three-way union as the sum of individual probabilities, probability of E and probability of F and probability of G. Then we subtract the probability of two-way intersections. So probability of E intersection F, probability of E intersection G, and probability of F intersection G will be subtracted. Finally, the probability of three-way intersection must be added again. So we sum up individual probabilities, we subtract two-way intersections for each dual combination, then we add the three-way intersection probability. Now we can practice the third proposition in another question. In this question, though it seems very lost, actually this is a rather easy question than easier question compared to the second question. It says an elementary school is offering 3 language classes, one in English, one in French, and one in German. The classes are open to any of the 100 students in the school. So there are 100 students in the school and there are 3 classes. It says there are 29 students registered in the English class, 26 students registered in the French class, and 16 registered in the German class. There are 12 students that are registered in both English and French, 4 that are registered in both English and German, and 6 that are registered in both French and German. And also there is another information. There are 2 students taking all 3 classes at the same time. So this is the information given by the question. Question asks us, if a student is chosen randomly, so among 100 students in the school, I am randomly choosing a student. What is the probability that she is taking at least one of the language classes? Okay. Now, with the given information, I don't know if you have realized or not, but there may be some students who are not taking any of these language classes. So there is a chance for a randomly selected student to take at least one of these classes. And in part B, again, it is asking what is the probability that the randomly selected student is not taking any of these language classes. So let us first solve part A, then part B. What is the probability that the randomly selected student is taking at least one of these language classes? Now, I have especially selected the languages as English, French, and German because I'm going to define these 3 events with these letters E, F, and G. So I am randomly selecting a student as an experiment. The event E is defined as my randomly selected student to take an English class. F is defined as the event of the randomly selected student is taking the French class. And event G is defined as the randomly selected student is taking the German class. Now, according to the question, since I know 29 out of 100 students are taking English class, and it is equally likely for me to choose any of these 100 students, the probability of event E is just going to be 0.29 by assumption. The probability of event F, because there are 26 registered students in French class, and for me it is equally likely to choose any one of the students on a random basis, my chance for the student to take the French class is 0.26. And it is going to be 0.16 for the German class because there are 16 students registered to German class. 12 students are registered to both English and French, therefore probability of E intersection F is 0.12. Probability of E intersection G is 4 over 100, 0.04. And probability of F intersection G is going to be 6 over 100, 0.06. Finally, since we know that out of 100, there are only 2 students who are taking all 3 classes, the probability of the 3-way intersection, all of the 3 events occurring at the same time, is going to be 0.02, because my chance to select such a student is 2 out of 100. Now we know this, and proposition 3, the probability of the union of the 3 events. In part A, the question asks me the probability that the randomly selected student is taking at least one of the language classes, which is E union F union G. Either E or F or G. So E or F or G, at least one of these classes must be taken by the student. So the question is asking me that probability, because the union means at least one of them occur, right? So the probability of the three-way union, according to the probability of the union of three events, is the sum of individual probabilities subtracting the probability of two-way intersections plus the probability of the three-way intersection. And all of these information were summarized in the previous page. So the result is going to be 0.51. So my chance to select a student from this school who is taking at least one of these classes is 0.51, which is not very large actually. Now, in the second part of the question is asking the probability that the randomly selected student is not taking any of the language classes. And that is the probability of E union F union G complement. Okay, so the event that the randomly selected student is not in any of these classes is the complement of the three-way union, right? So the complement of the student to take at least one of these classes is to take none of these classes. So the probability that the student takes none of these classes is going to be calculated by subtracting the complement events probability from 1. Okay, so remember, the complement of complement is equal to the set itself. So if you have the complement of the complement, you get the original set. So 1 minus probability of the three-way union gives us the probability of the complement of the three-way union. And that is going to be 1 minus 0.51, that is equal to 0.47.